Hi everybody, welcome back. This is lesson 12, unit 1, lesson 12. I just want to add on a couple things to the heating and cooling curve discussion. So if you all wouldn't mind taking out a sheet of paper, you can just label it lesson 12, and I'll be collecting these tomorrow. So you need your own sheet of paper to have this on, not on your notes. Make sure it's on your sheet of paper. One of the things I want to talk about is two new sort of terms that we can actually label our two flat parts, whoops, of our curve here. Uh-oh, my tray's not working. So this first flat part here, we call that the heat of fusion. And again, you could just sketch your curve with your two plateaus and label your first plateau heat of fusion. We abbreviate that HF, and it is a constant for a given substance. So for water, this is on table B. It is defined as the energy needed to melt 1 gram of ice when it's already at its melting point, okay? It's the energy needed to melt 1 gram of ice. You may write this down too as the definition. Of whatever, solid. At its melting point. Okay? So the energy it takes to go from here to here, that's your heat of fusion, when you're already at your melting point to when you're done melting. Up here from D to E, or again that'll be your second plateau, we call that the heat of vaporization. And that is abbreviated HV. And again, for water, that's also on table B. I think for water, the heat of fusion is about 334 joules for every gram of ice. And for heat of vaporization, it's 2,259 joules per gram. So you can see, at least for water, that it takes a lot more energy to boil, to turn it into a gas, than it does to melt it per gram of the substance. So again, heat of vaporization up here is the energy needed to boil or to turn 1 gram of liquid water into a gas once it's at its boiling point. I'm just going to have to abbreviate at BP. Yeah, my head's going to be in the way there for sure. So once you're already at the boil, it's the energy it takes to go from here to here, okay? And you would notice whatever this substance is, that is also a greater value than here. Not because it's at a higher temperature, but because the line is longer. The heat of vaporization line takes more time, takes more energy, if you think of this as energy added, than the heat of fusion. So those are two new terms I wanted to talk about. I also wanted to talk about endothermic and exothermic phase changes. So if we think of our curve, we have our solid, our liquid, our gas, and let's think about going up the stairs. So from solid to liquid, liquid to gas, or even if you skip over a step, solid to gas, okay? All of those phase changes. How do you make ice melt? How do you make water boil? How do you make dry ice sublime? What you really have to do to make each of those phases happen, those phase change happen, is add heat. So phase changes that involve going up the stairs on a heating curve are endothermic, right? You have to add energy or add heat to make them happen. Just like in the morning when you have to walk up 4 flights of stairs to get to your locker, right? That takes energy. So all of those phase changes take energy as well. But at 3 o'clock, when it's time to go home and you're flying down the stairs, it takes a lot less energy. In fact, you're releasing a lot of energy because you're woo-woo excited to go home. So going down the stairs, gas to liquid, liquid to solid, or maybe even deposition, gas to solid, Those are not energy requiring, those are energy releasing. You're exiting the building, and those are exothermic, okay? So sometimes questions like that come up, and I know that we didn't mention those in the video yesterday. So I'd like you to have heat of fusion, heat of vaporization defined on your paper and labeled on a curve. Again, remember this is your HF, heat of fusion. This is your HV, heat of vaporization. And I'd also like you to have an idea of what the endothermic phase changes are. You should write those down, the endothermic ones here, going up the stairs, and the exothermic phase changes going down the stairs. Have a great night. We'll see you in class tomorrow. Bye-bye.